Hey, welcome to 12 Tone. Harry Partch was an interesting fellow. He was a music theorist, a composer, and an instrument maker in the mid-20th century, and he had dreams of changing the landscape of modern music entirely. He felt we'd fallen too far into routines and traditions, that we were valuing technical skill over feelings and emotions, and that the very foundations of our musical tradition had become rotten. While his ideas never really caught on with the public, his explorations of tonality and intonation help reveal many of the limitations of our modern systems, and in order to understand his work, we first need to understand his greatest enemy, equal temperament. We've covered this before, but briefly, equal temperament is the idea that if two pairs of notes look like they're the same distance apart, they should sound like it too. For instance, F to F sharp is a half step, and so is F sharp to G. In an equal tempered system, the only difference between those two is the starting note. The distance is identical. And while that seems like an obvious result, it's actually a relatively recent idea. Even as late as the 18th century, there were other methods in common usage because equal temperament has a problem. Its intervals are all out of tune. You see, when we hear a note, what we're really hearing is the specific frequency of a sound wave, and when we hear two notes, our brain does a quick calculation to determine the ratio of the frequencies between them. For instance, the octave is a doubling in frequency, so we hear it as a ratio of 2 to 1. We tend to like it better when the numbers involved are lower, but in equal temperament, the ratios get real messy. The octave is exactly right, but everything else is at least a little off. Compare that to another older system, Pythagorean tuning. Pythagorean tuning is what's called a just intonation system because all of its intervals are whole number ratios. Pythagorean tuning is built to emphasize the perfect fifth, which has a frequency ratio of exactly 3 to 2. In order to do that, though, it has to sacrifice consistency. F to F sharp is now about 20% smaller than F sharp to G, even though they're both supposedly half steps. Partch didn't like this method either, though, because while we do get whole number ratios for all our intervals, many of them are quite large. For instance, a Pythagorean major third would have the ratio 81 to 64, whereas a truly just major third should be the much simpler ratio of 5 to 4. Plus, Partch wasn't a huge fan of the 12-note system anyway, so he decided to just make up his own rules, starting with what he called a tonality diamond. A tonality diamond is a way of laying out all the possible ratios of numbers up to a certain point. Well, actually, since doubling just changes octaves, and Partch still accepted the idea that notes an octave apart were harmonically equivalent, he only really needed to use the odd numbers. The even ones were just octaves above those. This is easier to understand with examples, so let's try constructing a diamond that goes up to 5. We can start by writing the 3 odd numbers on diagonals like this. These will be the tops of our ratios. Then we just add in the bottoms going diagonally the other way, and voila, every possible ratio between 1, 3, and 5. We can then multiply and divide by 2 a couple times to get them all in the same octave, and our diamond is complete. Another way to look at it is as a collection of triads. Going along any diagonal in this direction gets us to a justly tuned major triad, while any diagonal the other way gives us a justly tuned minor one instead. It also gives us a set of notes that we can turn into a scale, but here we find a bit of a problem. There's these huge gaps at the beginning and end. We start by jumping up a minor third, and that's a huge chunk of potential frequencies we're just skipping past. This bothered Partch, so he decided to include a couple extra notes to help round things out. Specifically, he allowed himself to use ratios of 9 and 15 since they were closely related to the 3 and 5 he'd started with. This gave him 6 new notes, which helped fill those giant gaps even if it sacrificed a bit of mathematical purity. Interestingly, it includes both the ratio 10 to 9 and 9 to 8, which are only about a fifth of a half step apart, but Partch still viewed them as different notes. This reveals a bit about his love of what's called microtonality, the use of very small intervals, which will come up again soon. Moving on though, Partch wasn't gonna stop at 5. No, as with many musical pioneers, he turned it up to 11. Specifically, he wanted to experiment with ratios constructed of the first 11 numbers, because that was the first set of ratios that he felt were completely alien to modern ears. From these we get this tonality diamond, which we can then turn into this 29-note scale, which I didn't bother notating because standard Western notation really isn't designed for this sort of thing anyway. Unfortunately, this scale also had too many gaps for Partch's taste, but this time he couldn't quite fix it by just adding a couple more factors. Instead, he had to go in and handpick the frequencies he wanted to fill those gaps with, resulting in a 43-note monstrosity that is now known as the Genesis scale, named after Partch's book, Genesis of a Music. It's a really microtonal scale. The largest gaps are only about 40% of a half step wide. It's a lot of notes to work with, so in order to help us out, Partch breaks the intervals up into 4 categories based on their approximate sizes. The intervals of power are the most stable and are made up of the octave, the perfect fifth, and the perfect fourth. In the middle of the scale between the fourth and fifth are the intervals of suspense, roughly equivalent to standard tritones. Outside that range lie the intervals of emotion, comparable to thirds and sixths in standard tuning, and right around around the roots of the scale are the intervals of approach, much like our seconds and sevenths. It may seem strange that Partch would choose a classification method that so closely resembled that of the 12-tone system he rejected, but I think it reveals something important about him. Underneath all the science and math, Harry Partch was still an artist, and his primary concern was making things that sounded good. He'd burn the whole system to the ground if he had to, but if there were already sufficient tools for the job, he was totally willing to appropriate those. He despised the compromises of equal temperament, but when his own system presented problems, like the large gaps around the root, he was happy to fix them so his music would work, because in the end what matters most is that the things you make sound good, at least to you. Anyway, thanks for watching. If you want to help make these videos possible, please consider supporting 12-Tone on Patreon or checking out our store. You can also join our mailing list to find out about new episodes, like, share, comment, subscribe, and keep on rockin'.